Welcome back to another video, our second to last one for linear algebra. Oh my gosh, we're getting so close. So this one is going to be a tad bit different because this is not something that you've seen before, but this is something that you can do that will help you when you start doing the Jordan canonical form. So this one, it tells you to predict the Jordan canonical form, and I'm pretty sure many of you are asking like, what? How can you do that? I mean, sure, you can predict the eigenvalues, but how do we know if our our Jordan canonical form is right? Well, it's fairly simple. So it all depends on the blocks and then the chain and then the effective eigenvalues. So let's go ahead and get started. So the first one is going to be a very simple one, 2 by 2 matrix as always. And so for this one, again, it's fair game. It's like usual, same old, same old. Find the characteristic equation, and then find the eigen values. Yeah, eigenvalues. So we'll have 1 minus lambda times 5 minus lambda. This is multiplied by 4 times -1, so plus 4, and that's equal to 0. So we'll get lambda squared plus 5 minus 6 plus 4, or lambda squared plus, this is supposed to be lambda, minus 6 lambda plus 9 is equal to 0. And this will be lambda minus 3 squared is equal to 0. So our eigenvalues are 3 with the multiplicity of 2. And so now what do? We plug in our eigenvalue into the matrix. So, so far nothing new. We've done this 1,000 times. So we'll have 1 minus 3 is -2, 4, -1, 2. And then here's where things get different. So now what you want to do is you want to find the rank, and because you find the rank, you can find the nullity. So for this one, we can see that row 1 is a multiple of row 2. So we know for a fact that the rank is going to be 1, and the nullity is going to equal 1. And so what our nullity tells us is the number of blocks in the Jordan canonical form. So if we have a nullity of 1, so that means there's going to be 1 block. And so that's pretty much it. All you have to do is just write your Jordan block, which will be, again, it's going to be a 2 by 2 matrix, and it's going to contain 1 block. And so, as always, the main diagonal will have our eigenvalues, and then our block will be this right here. And so our block is, like I mentioned in the lecture, it's a k by k. So because we have 1 block, nullity of 2, or no, because we have 1 block and we're working with a 2 by 2 matrix, then that block will be a 2 by 2 matrix as well. So our block will be just this portion here. And as we continue with the examples, hopefully you get an idea of what a block looks like in terms of like a 2 by 2, 3 by 3, so on and so forth. I think the highest I have here is a 3 by 3, but I could be wrong. So let's move on to the next example. The next example is, now we have a 3 by 3 matrix. Wow. So the good thing is that we have a 0 here, makes our lives easier. So we can just go along this vertical column here. So our characteristic equation will be 1 minus lambda multiplied by -5 minus lambda times 7 minus lambda minus plus 36. So this is going to equal to 1 minus lambda times -35 plus lambda squared plus 2 lambda plus 36, or this will be lambda squared plus 2 lambda plus 1, which is the same thing as lambda minus 1 quantity squared. So our eigenvalues will be lambda is equal to 1 with the multiplicity of 2, and then this one will be also 1. So this will be lambda is equal to 1 with the multiplicity equaling to 3. So we have a multiplicity of 3. It is possible to have defective eigenvalues because we have a multiplicity, but we'll see what happens. So when we plug in our lambda is equal to 1, we will get -6, 2, -12, 0, 0, 0, 3, -1, 6. And so again, we can clearly see that the second row is a multiple, or the first and third row is a multiple of the second row. So for the first one is you just multiply by 3. The third one, you just multiply the second by 6. 6? -6. My bad. Oh, the other one's -3. So we will have a rank equaling to 1 and a nullity equaling to 2. So again, our nullity is equal to 2. So that means we'll have 2 blocks in this 3 by 3 matrix. And so our Jordan canonical form will be again 1s across the diagonal, and then this portion will be 0. So we want 2 blocks. How do we create 2 blocks? Well, what we can do is we can have 1 by 1 block and 1 2 by 2 block. And that is the only possible way you can do it. You don't necessarily have to do it like this. You can also do it like this. So we have a 2 by 2 and a 1 by 1. And so it's pretty much however you like it. I like to have a 1 by 1 at the top, and then the 2 by 2 will be at the bottom. So this will become our Jordan block. We have our 1 by 1 here, and then our 2 by 2 here. And again, you can also do it the other way. So we have 1 0 0, 1 1 0, then 0 0 1. We'll have our 2 by 2 block here, and then our 1 by 1 block here. And so the number of blocks, it just tells you how many total blocks with respect to that eigenvalue we're gonna have. And so our last example will give you a much more clear idea. And so again, it's the same thing. The only difference is we're going to deal with the 4 by 4 matrix. We haven't done a 4 by 4 in a long time, but this is going to be easier again because we have zeros here and here. So we're just going to go down this vertical line, or this second column. And so our eigen, or not eigen, our characteristic equation will simply be, as a matter of fact, let me rewrite this entire thing. -8 minus lambda, 9, -6, 6, 0, 1 minus lambda, 1, 0, 0, -1, 3 minus lambda, 0, -15, 15, -10, and 11. And so this is going to give us, maybe, actually take that back. We're not going to go along this one. We're going to go along this one. This is going to give us 6 times the determinant of this one, because we'll have our -15. So this one will actually make it easier. 1 minus lambda, -1, 15, 1, 3 minus lambda, -10, and then plus, minus, plus, minus. So minus 11, it's supposed to be an 11 minus lambda. Minus lambda multiplied by the determinant of 8 negative lambda 0 0 9 1 minus lambda -6 1 3 minus lambda. And because I did this, we can just, the determinant for the 3 by 3 will be easier because we can just use the first row. We use a highlighter. We can use the first row for this one, first row for the other one. So we only have to worry about one. And so after you do all of that, you should be able to get 1 minus lambda times 3 minus lambda plus 1 multiplied by negative 90 minus negative 88 plus lambda squared minus 3 lambda. And then after further simplification, you will get lambda minus 2 quantity squared times negative lambda plus 1 times, or not quantity, cube. And so our eigenvalues would be lambda is equal to 2 with the multiplicity equaling to 3 and 1. So now again, just put in our matrix back and then find our Jordan block. So for the first one, actually, the lambda is equaling to 1 case. Well, we know that that's going to have a multiplicity equaling to 1. So that means it's just going to be a 1 by 1. So we don't, this one's okay. This one would just have one eigenvector since the geometric is equal to the algebraic. So we can just go ahead and start writing our Jordan block. It's going to be a 4 by 4 because our matrix A is 4 by 4. So it's going to be a 1 and then zeros all the way down here. So now for the lambda is equal to 2 case. Well, when we plug it into our matrix, we will get negative 10, 9, negative 6, 6, 0, negative 3, no, take that back, negative 2, I can't add, 1, 0, 0, negative 1, this will be 1, 0, negative 15, 15, negative 10, and 11. So for this one, we can't really see, maybe, no, yeah. So for this one, we can see that it is possible for the first row to zero out the second, or not second, the last row, but the second and third row, they look like they can't be zeroed out. For starters, you can't zero out this portion here. So this tells us that we will have a rank of 3 and a nullity equaling to 1. So again, we have a nullity equal to 1. So we will have 1 block in our Jordan. So again, what does that 1 block mean? Because this is 1 block, that means our block will be a 3 by 3. So that means we will use a different color. This is 1, right? No, 2. So 2 along the main diagonal, and then 0, 0, and then create our Jordan block like that. And so this is our answer. We are predicting it, and for a fact that this is going to be true because of our, what do you call it, our nullity and what we got. So this is our 3 by 3 Jordan block. Again, there's more than one way of finding or rewriting this. The Jordan block or the Jordan canonical form is not necessarily unique for reasons as you can write this in different ways. And so 0, 0, 0, 1, 0, 0. Wait, is it 1? Yeah, it is 1. Okay. So yeah, this is now our 3 by 3 Jordan block. And then our 1 by 1 is right here. Yeah, that's pretty much it for this video, and I'll see you in our last video.